Okay, well, thank you very much to inviting me to be a participant in this very nice program. And today I will speak about a ongoing project with Nathan Ilten from Simon Fraser University in Vancouver and Alfredo Nájera. And I will get to the slogan or what are we trying to do. Nathan is an algebraic geometer. Alfredo is essentially a cluster algebraist, and I am a representation theorist. So we are trying to sort of merge these words in some way. Why I put this title to this talk? Well, if you want, from a representation theory point of view, what usually puts the beginning of the representation theory of finite dimensional algebra or quivers in the 70s, essentially, when starts sort of in the 70s with the works of Gabriel, Auslander-Reiten, Gabriel, who introduced the quiver representations and the quivers associated to every finite dimensional algebra, Auslander and Reiten, when they studied almost split sequences and what was now known as Auslander-Reiten theory. And also you have the Kiev school, who have done a lot of work, for instance, in the Brouwer-Thrall conjectures. Then the time passed, and in the 80s, but also in the 70s, Gabriel showed that the hereditary algebras of finite representation type are classified using linking diagrams, which was quite a surprise and gave an immediate relation between finite dimensional algebras and classical Lie theory, right? And once again, the linking diagrams were arriving. In the 80s, there was a lot of development with tilting theory. We can name many people, but let me name Sheila Brenner and Butler, Michael Butler. Also Happel and Ringel. Who developed tilting theory, and Baumgart's using covering theory was able to classify completely all the finite dimensional algebras of finite type, as I said, using covering theory and local. So you can describe locally all the quivers and relations of these algebras. Although his theorem is a bit technical, this gives you a complete classification of finite dimensional algebras of finite type. In the 90s, there is many people that I should mention here, but let me mention Skovronsky, also Ibrahim Assem, who were big. I mean, and there are many other people, Flavio Coelho, which there was a huge, of course, Ringel again, a study. So representation theory came to study tame algebras, and we were trying to describe Auslander-Reiten quivers and so on. But as we all know who we are here, and we have heard this many times, in the 2000s, the shift of the study of representation theory changed radically because we started trying to understand cluster algebras using representation theory. Yeah, so the shift was to categorify cluster algebras. This is the aim, and many people I need to mention here for of course, Garland Keller, Eden Reiten. I need to say she has been giving us food for thought during all these years. I mean, she hasn't stopped a little bit. Brittany March here present, she has done a lot of work for this. And essentially, I think most of the people that are present in this room have been helping a lot with the categorification of cluster algebra. And this is a process that still is ongoing. I mean, we have seen the lectures of Bernard Keller during the last weeks, in which he showed us that, okay, we still want to categorify cluster algebras, in this case with frozen coefficients. But all the study of cluster algebras has given us, in representation theory, and I say as a representation theorist, studying cluster algebras in detail give us new theories that today are the main subject of study. And if you go to any conference, you would hear two things quite a lot. First, tau tilting theory. Guarachi, Yama, and Ilten have also higher homological algebra, and this is essentially due to Yama. This appears, so okay, there is a bit of delay between the two. This is 2008, this is 2012 when they appear to the archive and so on. But I mean, both of these theories that are now central in representation theory came up from the study, the deep study of cluster algebras. Now, let me now speak about tilting theory, tau tilting theory, sorry. I will concentrate in tau tilting theory. Tau tilting theory arises as a theory in, okay, studying cluster algebras, we knew that there were mutations, and we categorified, for instance, all the acyclic, skew symmetric cluster algebras using cluster categories. But then Ingalls and Thomas have done an incredible series of bijections between not only clusters, but also objects in the module category, like torsion classes and what they call support tilting modules. And then Arachi, Yama, and Wright realized that actually this was unveiling a much deeper structure that was lying there in front of our eyes for all these years, and actually it works very, very well. And tau tilting theory in other ways is a way to complete classical tilting theory using with respect to the notion of mutation. Okay, so let me give a series of definitions because I want to get to some theorem now. Eventually, not now, but this is due to Adachi, Yama, and Wrighton all together. Actually, they were all together. So, okay. Let me give you the setting. For me, A is a finite dimensional algebra over any field, over a field. Okay, and when I write this big K, this like a bold K, this is a algebraically closed field. And I would need that later. I will speak about module categories of algebras, which are essentially the category of finitely generated right A modules. And then tau corresponds as an application. This is not a functor, not at this level, at least, is the Oslander-Wrighton translation. It's the Oslander-Wrighton translation in mod A, and if I take any object in mod A, the cardinal of M is essentially the number of indecomposable direct sums, isoclasses of indecomposable direct sums. Okay, and I would need this for this definition here. So, what is the definition of what does tau tilting theory study? Well, tau tilting theory study tau tilting pairs. Okay, and the definition is the following. So let M to be an object in mod A and P projective A module. We say that first M is tau rigid if M tau M is 0. So there are no maps from M to its Auslander-Ritten translation. A pair MP, recall that P is projective, is tau rigid if the M is tau rigid and hom of P M is equal to 0. There are no maps from this projective. Essentially, the top of P is not composition factor of M. By abuse of notation, we will say that a tau rigid pair MP is indecomposable and I said again, this is by abuse of notation, if essentially the number of isoclasses of indecomposable direct sums of N plus P, I can put it even like this, is 1. So either M is 0 or P is 0, and if the one which is not 0 is essentially indecomposable if we consider it basic. And finally, we said that tau rigid pair is tau tilting if the number of indecomposable direct sums of M plus P is equal to N, where N is essentially the number of non-isomorphic indecomposable projectives, or which is the same as the number, if you want to think in quiver terms, the number of vertices in our quiver. Okay? I mean, that's why I put here isoclasses of indecomposables. Yes. Is M plus M indecomposable? At oral, yeah, I might be thinking that is basic. I assume whenever I talk, assume that M is basic. Yes. In order to avoid any problem. Yes. I mean, M plus M has only one. If M is indecomposable, M plus M has one isoclass of indecomposable direct sums. Right, but you didn't want to find it indecomposable. No, a priori, no. I mean, you could just say if M plus M is indecomposable. Yeah. That's why I also said that this is an abuse of notation, right? Yeah. I mean, or yeah. So why why we care about tau tilting theory? Well, there are many reasons, but one theorem by same people, Arachi, Yaman, Reiten, showed us that first, there is a well-defined notion of mutation. What I mean by this is, I mean, if suppose that MP is tau tilting, and suppose that M prime, let's put it like this, M plus M prime is tau tilting, and M, 0 is indecomposable, of course, tau rigid. So there exists a unique pair that indecomposable tau rigid pair M tilde P tilde, such that M plus M tilde P plus P tilde is tau tilting. And the same happens if we consider the case 0 P prime, and here we would have P prime plus P. Okay? So we have a really good notion of mutation. And the second is, and why I'm speaking about this when I say cluster algebras in my title, is because if A is a skew symmetric cluster algebra, or of finite type, then there exists an algebra A, and this is not unique. There exists a finite dimensional algebra, dimension such that we have two correspondences. On the first, the number of clusters, they are in one-to-one correspondence with tau tilting pairs. And the second is that the cluster variables they are in one-to-one correspondence with indecomposable tau rigid pairs. Moreover, the mutation at the level of cluster algebras commutes with the mutation of tau tilting pairs at this level. I mean, if you take a tau tilting pair, you do a mutation, and then you take from the first tau tilting pair, you take the cluster, and you do the mutation in the same summand, you get to the same place. You get the same cluster. Okay, the cluster associated to the mutation of the tau tilting. But as I said here, if you have if you have a cluster algebra of finite type or skew symmetric, then you have an algebra, a finite dimensional algebra. But as it happens, there are many finite dimensional algebras, which as of today they do not have any cluster counterpart. And this is sort of our aim. So the long-term aim of this collaboration is to find a cluster-like algebra associated to every finite dimensional algebra A. Okay, when I say cluster-like algebra, well, this is one of the things that we still need to figure out completely. But one thing that for sure we want to have is that this cluster-like algebra needs to be a commutative algebra, and we want to construct this as a coordinate ring of some algebraic variety. Actually, this is our aim, and essentially today. So this is really, and we want to do this using deformation theory. And the theorem that I want to present today is check that this is possible for cluster algebras of finite type. Yeah. Yes, I think so. Yes. I don't think so. Okay. I think if your quiver is very, very bad, then there might not be any. Maybe, or maybe let's say acyclic. Acyclic is true. Is true for sure, and there are others. I mean, definitely for Grassmannian cluster algebras, this is also true, and for yeah, more or less. If it is true that for every skew-symmetric cluster algebras there is such a finite dimensional algebra, and there are definitely equivalents to which the obvious potential is perfectly fine. Right. So that means you see the different non-obvious potential. Maybe, yeah. So yeah. Maybe I overstated that result. It might be a possibility, yes. But what is sure is that for every cluster algebra of finite type, we have such an algebra, right? So what we want to do is actually check if for the cluster algebras of finite type, a construction, a recipe that essentially Nathan came up with and Alfredo came up with actually works. Okay, and this is the main theorem of today, and saying yes, this can be done. We can recover using deformation theory the universal even cluster algebra associated to every cluster algebra of finite type. And for that, we will use the tau tilting theory that we have, but actually a combinatorial tool. Before I go further, I want to mention that, let's say this is not the first time that one wants to do such a thing. I mean, if one looks at the CC algebras defined by Cerulli-Irelli, Labardini-Fragoso, and Ian Schroer, these algebras, I mean, using the cluster character into what they call the tau-reduced components, which are associated to finite dimensional algebras, and build a commutative algebra associated to these finite dimensional algebras. The main difference here is that our approach is somehow more global, in the sense that we are not taking, we we are not getting polynomials for each one of our tau-rigid objects after we finish somehow. Okay? Okay. So that being said, how we wanted to do it? We want to do that using deformation theory. And for that, let me define, there is a nice definition of a simplicial complex, the tau tilting simplicial complex. Essentially, the zero cells correspond to the indecomposable tau-rigid pairs. Okay, and the K cells will correspond to the sets M1, and I will call this actually the set of vertices, and we denoted this by a V. MP, M1, P1, MK, PK. Okay, and here they are non-isomorphic 2 by 2. Okay, so I take one isoclass for each one, so I have a number well defined. And this is this inside of B, such that, as you imagine, we have that the sum from I equal to 1 up to K of MI sum up to K of PI is tau-rigid. Yes. Yes.
Bernard Keller said, did Hipolito really want to write cluster algebras of finite type and not finite dimensional algebras of finite type?
Where? And the aim is.
What you're saying that you're going to start with something like a thinking pillar and see if you can
reveal the cluster algebra, yes.
Right. So you're not going to start with something for which the cluster algebra didn't already exist.
For the today, no. Today I would take something in which the cluster algebra already exists to check, to verify, because we have a recipe, and I will tell you the recipe in a bit. But we want to do in such a way that actually the cluster structure is not actually needed, and this is sort of the punchline here, is that in the recipe that we have, we will only take into account the tau tilting simplicial complex of a finite dimensional algebra, right? And we will suppose that this tau tilting simplicial, so this finite dimensional algebra has associated a cluster algebra of finite type. So one can think, for instance, to the hereditary algebras of finite representation type. Yes, and these have associated a cluster algebra of thinking type. And we will see that using the tau tilting complex, we can recover the cluster algebra. Does it? Yeah. Does it answer the question? Yes? No?
I think they must look for
yeah, or finite type. I mean, it could be of type B or C or G, right? So for these cluster algebras, there are finite dimensional algebras which for which the tau tilting theory looks. I mean, and this is a one-to-one correspondence, maybe not at the factorial level. I mean, it's not a proper categorification. If you look, for instance, the categories of species of a weighted quiver, but you have still the correspondence, right? Well, so we have this this tau tilting simplicial complex, right? And Of course, I mean, it would be finite. This implication complex will be finite only when you have finitely many indecomposable tau-rigid objects, right? And this would be finite only for what is called tau-tilting finite algebras. But there is a really nice result. This is a theorem by Demonet, Iyama, and Hasso. Actually, they're all together. That says that, and I will call this K of A. Okay, so A, this is the simplicial complex associated to A, that K of A is isomorphic to the n-1 sphere, where recall n is the number of vertices that I have in my quiver, if and only if A is tau-tilting finite. Okay? If and only if this is tau-tilting finite. There is, for those who know about it, there is a very natural realization of this simplicial complex, which can be done using the G vectors naturally associated to every tau-rigid object. Okay, which is also deeply related with the scattering diagram associated to each finite dimensional algebra, which always exists, right? But now we are taking only the combinatorial properties here. Well, so from now on, I will concentrate myself. From now on, A is always tau-tilting finite. Okay. Okay. For that, I need to recall, and I will go into waters which which are less explored by me, which are the notions of, I will need to speak about deformation theory, and Stanley-Reisner rings. But okay, I will start with deformation theory. So what is a deformation? A deformation, the definition is the following. For this, let S to be a K, so it's a commutative ring, a commutative algebra over an algebraically closed field over K, okay? And then I can take the variety X to be the spec of this guy, all right? So essentially, a deformation is a Cartesian square which has the following shape. We have X, we have a map to a point or spec K, right? And we have that this map, here we have a family, and here we have Z, and here we have a morphism P, which is flat. So essentially, what is this telling us? It's telling us that the deformation theory of deformations of X is that we can have a set here of parameters we have a set of a variety in general of which give us parameters, And then here what we have is that for each point in set, we will have a variety such that for one distinguished point, which is the image of this particular point, star here, speck of k, we recover this k here. In some sense, it's some kind of moduli space that we are having, in which in one distinguished point, we are recovering x. This, it's a bit abstract. One way, and at least for like for me personally, one way one can see this is that suppose that S is actually a quotient of a polynomial ring x1 xt over some ideal generated by f1 fk. Okay, so the idea of a deformation would be to consider x could be the spec of, for instance, of a quotient of another polynomial ring, say x1 xt, but then we continue with a1 at, right? So we have many more variables, and we quotient by so an ideal generated by f1, big f1 fk, where we ask that f x1 xt and zeros, if we put zeros in the parameter for f, this is the same as the original value of the polynomial fi in the original variables. Okay, so in a sense, what we are doing is we are taking new, so this is a big variety, this would be this guy, and at each valuation of your parameters, you would get one variety, and in particular, when all the parameters are zero, then you are recovering exactly the variety that you started with. Okay, and then where I can continue. Okay, let me continue here. Yeah, there are technical, yeah, it's not this general, but it's like an intuitive idea, because you need conditions in order to make the map P flat, if I'm not mistaken. Yeah. Now, in order to do this, we want to have a natural. Okay, so we want to apply deformation theory, but we need to deform something, right? This is an important bit, and which is the kind of ring that we want to deform. Well, this would be the Stanley-Reisner ring of my simplicial complex. So what is the Stanley-Reisner ring? So first we start with a let K be a finite simplicial complex. Okay, and take the Stanley-Reisner ideal of K is defined as follows. I sub K is essentially generated by the product of okay, this is an ideal which is first inside the polynomial ring K x1 xt, where T is the number of vertices I have in my simplicial complex. Okay, and this ideal is generated by x1 xk such that x1 xk, so this is the product right here, xk is not a phase of my simplicial complex. What I mean by this, so the simplicial complex has this nice combinatorial structure. So what I'm doing in this ideal is I'm killing, I generating this ideal by taking the products of the things that are not compatible with each other. Okay, and the Stanley-Reisner ring the Stanley-Reisner ring S sub K, as you imagine, is the polynomial ring quotient by the Stanley-Reisner ideal. So this ring is capturing actually the combinatorial structure of our simplicial complex, right? Now, well, in particular, we have, so let me say that S of A for me is the Stanley-Reisner ring of my finite dimensional algebra A, where the Stanley-Reisner ring is constructed using the Taut tilting simplicial complex that we have. Okay, so right. So one more thing, because before I go, and I can actually put it here. Is that another definition, sorry about this, which we say that a deformation is semi-universal if the following diagram commutes. What I have, okay, I want, so what is my deformation? My deformation is pi, which goes from x to z. So on the one hand side, I have a deformation that goes here to z, goes here to x, and we have pi, which this is flat, such that for any other deformation, x tilde, z tilde, right, and pi tilde, there exists a map pi tilde phi, which is Cartesian. Okay? Yes? Yes, please. Yes. Yes.
We want a monomial for every vertices that is not a phase.
Yes.
Not just for the initial segment in the sequence 1 up to t of
Yes. Yeah. 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 Sorry. This is not. Yeah. This is not the order. I mean, this would be x prime somehow, right?
You don't need to introduce an arbitrary number into the program. And then the generator, then the generator is the idea of
yes.
P1 of x bk, where P1 of x bk.
Yes.
But I don't think you have to write that.
Yeah. Yeah. There are better ways to write this down. Yes. Sorry. So this is an idea. It's like we can sort of for every other deformation we can map it into this original, and it's semi-universal because actually this morphism of deformations is in general not unique. Okay. And now I think I can actually give you a theorem of which relates to our aim, and the theorem is the following. And this is joint work with Ilten, Jera. And is okay. It is the following. Let A be a finite dimensional algebra of finite type, hereditary algebra, sorry, hereditary algebra of finite type. And a finite, yeah. Then there exists a torus H. Let me recall it, how to put it. And a H invariant semi-universal deformation of course S of A of my Stanley-Reisner ring, which is of the form pi, which goes from the spec of the universal cluster algebra associated to this guy to, and here actually, if I didn't make a mistake, is to an affine, yeah, where T, this is the affine space in which T is the number of vertices that we have in our simplicial complex. So it's the origin. In other words, what I say that this gives us what we want. Well, pictorially, we are getting the following thing. we are getting AP here, the affine plane. And here we are having a variety, which is not other thing that spec of the universal cluster algebra. For this universal cluster algebra is the universal cluster algebra associated to this finite dimensional algebra. Okay, so we have a finite dimensional hereditary algebra, which is associated to a Dynkin type. So we have a cluster algebra associated to this Dynkin type. And we have a semi-universal deformation. So we have pi, a flat family, a flat morphism from here to here, such that at 0, what I have here is actually spec of the Stanley-Reisner ideal. And then in 1, this is 0, and in 1, actually I am getting the cluster algebra, the traditional cluster algebra associated. So okay, the spec, sorry, the spec of the cluster algebra. Here. Okay, so let me do an example. Shoot. Sorry, repeat. Well. Yes. Yes. Cheers. So I'll do. Yes. Yeah. That's exactly it, and this is exactly the example that I will do now. Which, of course, as you imagine, is A2. So I have this thinking quiver, right? And then actually the simplicial complex associated to S2 is of the form like this. Okay, the slender right hand quiver is this guy. So S2, P1, S1 here. The shift of P2, shift of P1. Okay, this is my simplicial. This is my simplicial complex, right? So what is the Stanley-Reisner? I would put the equations of the Stanley-Reisner ideal, and I will call this actually 1, 2, 3, 4, 5. I will enumerate this in this way. And actually, the Stanley-Reisner ideal of A, the equations that we have is x1, x3 is equal to 0, x2, x4 is equal to 0, x3, x5 is equal to 0, x4, x1 is equal to 0, and x5, x2 is equal to 0. Okay? But for those that know about universal cluster algebras, we have that the set of equations are x1, x3 is equal up to some change of numeration in the universal coefficients, T2, x2, x2, x4, T2, T4 plus T3, x3, 3, x5 3t5 plus t4 x4 x4 x5 is t4 t4 t1, sorry, x4 x1 t1 plus t5 x5 and x5 x2 is t5 t2 plus t1 x1, and when we put t equal to 1 we recover maybe I will put so I will put it here. Maybe okay. A is the classical cluster algebra is x1, x3 is 1 plus x2, x2 is 4, 1 plus x3, 3, x5, 1 plus x4, x4, x1, 1 plus x5, and finally x5, x2, 1 plus x1, right? And here we can see, and actually the interesting thing is that the universal cluster algebra really comes from this deformation theory. One thing that to finish, I didn't have time to speak about many aspects of the work that we are doing, but one thing that I want to conclude is that if one knows a bit about finite type cluster algebras, one can argue is, okay, this might be wrong because B and C actually have the cluster algebras type B and C have exactly the same Stanley-Reisner ring. So actually they have the same simplicial complex associated to them. So what about these cases? Well, this comes from, actually one can construct what is called the cotangent homology of this ring. And for the case B and C, the second of this group is not 0, meaning that we have different irreducible components. Okay, and actually this torus, which fixes somehow this torus, actually, and here in order to prove this, we are using the fact that we already have the cluster algebra because we are choosing this torus to be the one that fixes the cluster algebra. These torus are sending the sort of the universal cluster algebra of type B and C to different irreducible components of this deformation theory. So actually, having complex which are called unobstructed will morally, I mean, even if we don't have at all sort of a formal way to say this, but morally, if you have a complex which is unobstructed, so this second cohomology group is 0, then we'll have essentially only one cluster structure, in some sense, possible cluster structure to define. And this is one of the things that we showed, is that for the cluster algebras of finite type, the only cluster algebras which have an unobstructed complexes are those which are skew symmetric, right? It's an if and only if. And then what happens with tau tilting finite algebras? Okay, what happens with tau tilting infinite algebras? Okay, this is work in progress, and this is what we aim for. For the first thing is that when our complexes are unobstructed, many things become easier. So it is there are many. We're using quite a lot of nice properties that cluster algebras have in order to prove this theorem. And so for all other tau tilting finite algebras, it's more tricky to choose what is the correct torus to get in order to have this commutative algebra. But we are having already some nice things. And okay, I can speak for longer about this, but let me finish here. Thank you very much.
I have some comments. The first one, fine.
Yes.
For the technical note, we cannot hear me.
Ah,
How is it now?
do you hear Emine when she talks?
Can you hear Hipolito?
Okay. I can read the comments otherwise.
Yeah, we can hear Hipolito. Okay, we can, then I can bring chat to you so that you can monitor it. Yeah, so you can look at the chat and then.
Okay. So I see. So technical comment from Nathan, who's actually the algebraic geometer and who knows better about all this, is that what I actually defined is versal deformation, not semi-universal. Sorry about that. To get semi-universal, you need also to require that the differential of the inducing phi at the distinct point is uniquely determined. And in case it's unclear, the formations are unique, albeit up to non-canonical isomorphism. So the point in what we recovered the universal cluster algebra from the cluster complex is unique up to plus additional information that we have about the torus action, right? And we are using, for instance, in order to prove this, many things about actually gradings of cluster algebras, which were defined by Jan Grabowski and stuff like that. And then okay.
Are there any questions?
And I will be repeating the questions aloud for those who are not in the room. Yeah. Sorry. So, well, where is how we can? Yeah. Yes. So the question of Lang was how you see the dimension of a Stanley-Reisner ring. The Krull dimension. I personally don't know. He wants to make sure that that ring is of dimension 2, the Krull dimension 2. I don't know. The Stanley-Reisner ring is of dimension 2. Okay. The Krull dimension is 1 plus the dimensions of a maximal simple. Simplex, sorry. In this case are of the dimension 1, because I mean this is isomorphic to a circle. So in this case it's 2. Yes.
Any other questions?
I can repeat the question. Okay.
What happens if you use principal coefficients?
What happens if we use principal coefficients?
You just set them to 0. What ring?
I mean, actually, we can do this for any coefficients somehow.
Well, you won't know what the ring is at 0.
Yeah. I don't know, really.
I guess my question is, there are smaller coefficient systems that give the Stanley-Reisner ring. For example, one.
I don't know.
Okay.
I don't know. Maybe. So the question was, what happens if we use principal coefficients instead of the universal coefficients? But I personally don't know. I would need to ask both Nathan and Alfredo. Yeah.
The second question is, have you computed the semi-universal deformation when A is linear A3 mod the long relation?
And what happens with linear A3 mod the long relation? Yeah. So in this case, we have compute stuff and it seems to be associated to SO105. Some kind of nice sugar variety is arising, but there are many things that are sort of not completely satisfying from a purely cluster point of view, in the sense that you don't always get. So actually, when you do this calculation, you can recover the cluster structure, because actually you can see which is the ideal. So you take the spec of the cluster algebra, you have this is a quotient of a polynomial ideal. So you can see which are all the generators of this ideal. We can calculate this. And then in particular, you can see which are the relations that have those which are exchangeable, right? When you are doing a mutation, you can recover sort of these relations there, right? As part of the ideal. And for this particular example, it happens that not always a mutation will have elements. So here we always have the binomial that we are having in the cluster mutation only has variables within the common cluster somehow, right? This is the classical definition of Fomin and Selevinsky. This is not longer true always, which is a bit unsatisfactory from a cluster point of view, but at the same time we are getting out of the cluster case. So we might, but yeah, it's this. Maybe Nathan has a further comment.
This is for the previous question.
The special fiber over the principal coefficients will be a toric variety, not Stanley-Reines scheme. Yeah.
Just still the last point. This SO105 is the whole family, the fiber over 0 or the fiber over 1?
Over 1. Okay. Yeah, because over 0 you always have the Stanley-Reines ring, which is always like highly degenerate. Yeah.
And let's thank Hipolito again.
Thank you very much.
Thanks everyone for joining.
Thank you very much.